So, welcome to the fourth session in this course, and now it is high time that we did a little bit of formalizing. So, we have been informally talking about inputs, outputs and systems all this while, and we have talked about the importance of abstraction. By now, I hope we are all convinced that abstraction has its merits. So, we need to complete that process of abstraction by making certain formal definitions. So, let us do that before we go ahead. What is a signal? A signal is a reasonable. Now, here I am being a little loose just in this part of the definition, but I think we all understand what it means. A reasonable function of an independent variable. Let me give you an example of an unreasonable function, which I just alluded to in the first session. So, x of t is 1 when t is rational and 0 when t is irrational. T is of course real. Now, for a mathematician there is nothing unreasonable about this function, but for a signal and systems engineer there is. In practical life, I am seldom going to come out with a function like this. No system will really generate a function like this. And also this function has many demerits. It is nowhere continuous, and leave alone the question of differentiability and so on. Although these functions have their merits in mathematics, we do not want to bring in such functions in our discussion, at least for now. By and large, functions that we would encounter in real life, or functions which could be called idealizations of those that we encounter in real life, are what we will accept as signals. I know that is a little vague, but I believe that is operationally adequate at this moment as a definition of a signal. What is a system? It is a mapping from signals to signals. So, now let me put down system and signal together. So, signal is a mapping typically from the set of reals. If you are talking about a continuous signal, continuous variable signal, it is a mapping from the set of reals to the set of complex numbers in general. Now, please, here I am jumping a few steps. All this while I have never really explained why I need to map time to a complex number, and right now I shan't do that, but I will just remember that real numbers are after all a subset of complex numbers. So, even if I have a signal which maps time to a real number, as you do for example in a voltage signal or in a force signal or in a pressure signal, you could also think of it as mapping time to a complex number, except that the imaginary part of the complex number is 0. After a while, we will make that imaginary part non-zero with good intentions, but we will postpone that for a while. However, we will keep that possibility open. So, we will say a signal is a mapping from the reals to the set of complex numbers. So, in that sense, now if you look at both these definitions here, the system is a mapping from signals to signals, and a signal is a mapping from the reals to the set of complex numbers. So, in some sense, a system is one mapping above another. A system is a mapping of mappings. A system is a mapping on mappings, one level higher. Of course, we have also talked about what is called a system description. A system description, now we will call it a little more flexibly an explicit or implicit relation between input and output. Of the system. And what are the inputs and outputs? The two parts of the mapping. So, we said the system is a mapping on mappings. The input signal is a mapping from reals to complex numbers. the output is also mapping from reals to complex, and the input and the output as composite entities have a mapping between them, which we call the system description. That mapping can be implicit or explicit. Let us take examples of both. An explicit mapping, which says that yt is, let us say for example, 5 times dxt dt. Clearly you know what the output is, and we shall use this convention in future. We will use, when it is not otherwise specified, we will use yt to denote the output signal and xt to denote the input. This is an explicit mapping. Why is it explicit? Because if I give you xt, there is a direct mechanism for calculation of yt. I can read off yt from xt being given. Let us take an example of an implicit mapping. In an implicit mapping, this relationship, though it is specified, is not a readout kind of relationship. So, I might have something like 2d squared yt dt squared plus yt plus 3 dxt dt plus 5 xt is equal to 0. Now, although you know here the relation between xt and yt, there is no readout. It is not easy to read out. Once I give you xt, even for all time or whatever, you need to do more work. You need to either solve an equation or work on an equation to come to a conclusion what yt is. Also, this is implicit for another reason. You need to do a little bit of work to separate the input and the output. Of course, here the job is very easy, because if you look at this equation, you can easily separate the input part and the output part. There is almost no effort there. You could simply say 2d squared yt dt squared plus yt is minus 3 dxt dt minus 5 xt. But then suppose you had an equation something like this. You had dyt dt plus yt times xt plus xt squared is a constant, let us say 3. This is also implicit, but this is inseparable. It's very difficult to separate yt and xt here. It takes more trouble. Now, we do not want to go any further to make distinctions on these description types. We just want to appreciate that there are all these possibilities in describing systems and system descriptions, and we shall be content if one of them is given to us. It tells us about the system. What we are trying to say is, we do not want a situation where I have to tabulate every xt yt pair. That we do not want. But that is what ultimately a system is, a mapping from the whole xt itself to the whole yt itself. So, in principle, you should have every possible xt tabulated and the corresponding yt tabulated. That is not what we want. We want something more compact than that, and that is what we are calling a system description. Could be explicit, could be implicit, could be easy to separate into input and output parts, may not be so easy to separate into input and output parts. Now, once we have a system description, we can start asking some questions about that system. For example, the first question that we can ask, suppose I perform 3 experiments on the system. In one experiment, I give it the input x1t and generate the output y1t. In the second experiment, I give it the input x2t and generate the output y2t. In the third experiment, I give it the input x1t plus x2t. In other words, I add the 2 inputs that I gave in the first 2 experiments, and I query what is the output. Now, For a large number of systems, it is possible that the output also has the same additive law. So, suppose we have a situation where for every such x1 and x2, if x1t plus x2t gives you y1t plus y2t, we then have the first system property, first characteristic of a system being established. So, you see, at this point, before I conclude this session, I want to bring in the notion of a system characteristic or system property. This is the first system property called additivity. The system is said to obey additivity if this is true. For every such x1 and x2, if x1t plus x2t results in y1t plus y2t, we say the system obeys the principle of additivity. Similarly, in the next session, we shall look at more questions that we can ask about the system and the system properties that we can infer based on the answer.